Hello AP, 8.2 Ionic Bonding. This is a topic where we have to focus on taking the metals and nonmetals and creating an ionic bond. We got a couple things we're going to look at as in trends. So let's get started. So consider the reaction, basic reaction, sodium chloride, probably the most famous salt out there in the world. You have sodium, the element, and the diatomic gas, it produces sodium chloride as a salt. Okay, this would not be aqueous because you did not put this in water or anything like that, so it's going to stay in solid form. Now, you're going to start to see some values listed after a balance equation, and this is called thermal chemical data. Okay, now let's break this word down. Thermal means the word heat, energy, okay? Chemical, obviously, reaction. So when these two elements came together and formed a compound, obviously you produce something new. You have a chemical reaction. Now what this means is delta H is the heat. The triangle means the change. So the change in heat, what happens is in the beginning, you have no heat, no nothing. You haven't done anything. And then you put these two chemicals together and you have this negative 410. Now remember what that negative means. It means that's exothermic, which means you lost heat, you lost energy, producing that salt, okay? And how do you know? Well, I showed you that video in, I believe, chapter 7, where sodium, the metal, came in contact with chlorine gas in a very bright, very bright reaction. And basically, it's almost like an explosion. And when you do have a explosion like that, you release heat. So that's why it's negative. Now, what's this little F and this little degree sign about? Okay, so let me make a little key up here. So that little degree sign, so delta H, little degree sign, means something called standard state. And you're going to see these two words pop up a lot when we get to chapter 5 and 19. It's called thermochemistry. Standard state means it happened at 1 atm, which means that is the standard pressure, and it happened at 25 degrees Celsius, which is called room temperature. Okay? So not only temperature, but I'm even going to put over here room temperature. It's 25 degrees Celsius. Then you have this little F, okay? And that little F stands for formation. I formed a salt. So it's the heat that was either lost or gained forming this compound. And in this case, for sodium chloride, it was an exothermic reaction. So this is called a thermochemical data equation. The thermal, the chemical, and all the data are in one line. This reaction is very violent, exothermic, as you saw in the video from chapter 7. We can infer that sodium chloride as a solid is more stable than its elements by itself. So because you lost energy, it's much easier to lose energy than to gain energy. So because it lost, it's actually more stable than the actual elements by themselves. Sodium lost an electron, becomes sodium plus 1. Chlorine gained it to become Cl minus. We know that. But now that we've learned chapter 6 and 7, what happens to the configuration? Well, sodium plus 1 now has a neon electron configuration, which means 8 valence electron when he had only 1. Chlorine had 7 valence and now has an argon configuration, which also has 8 valence electrons. Okay? That is, both sodium plus 1 and both Cl minus have an octet of those electrons. Now, you got to remember from chapter 7, don't start losing that information from chapter 7 just from last week. Properties, okay? Electrons transfer to form oppositely charged ions occur when one atom very easily gives up the electrons, and we already know metals will love to do this. Metals have very low ionization energy, so that's why they lose electrons very easily. Nonmetals have very high ionization energy, because they don't want to lose electrons. They want to gain electrons. So we got to take maybe a little reminder from chapter 7. Ionization energy is always positive because you need energy to lose electrons. Okay? But then you have nonmetals that have very high electron affinity. Now, electron affinities can be positive or negative. Most of the time, negative. And for nonmetals, you have very high negative values because they are very happy. They are very happy to accept that electron that you're pretty much trying to force on them. And why? Because they have more protons than metals. Okay? Nonmetals always have more protons than metals, and that's why they're very willing to accept those electrons, because they have a very strong attraction between the protons and the electrons. Okay? So sodium chloride, a typical ionic compound, metal has low ionization energy, will transfer that one valence electron to the nonmetal chlorine because he's very happy to accept it. Now, when you draw the structures, we're now going to start to draw. We only draw ionic compounds probably one time in AP, and that's it, and it's in this chapter. Because the majority of the compounds and molecules that you come across it in life, you wear it, you eat it, you breathe it, they're all molecules. They're all molecular compounds. So the rest of the chapter, the rest of the course is going to be focusing on molecules because that's the majority of everything that we come into contact with. However, we do have to learn how to draw some ionic. Ionic compounds, Lewis dot structures, okay? You draw the Lewis dot structures for the positive ions, and you have to draw brackets because you have to show that that metal lost electrons. And for the negative, same thing, you draw the brackets because you have to show that he gained an electron. So if I just had sodium with his one valence electron, and then what happens is when he loses that one electron, well, now he looks like, according to his structure, he looks like he doesn't have any valence electrons. Well, he does, because now he has a neon electron configuration. So he has valence electron. He has 8. But you have to show that he lost an electron. So we put that symbol in brackets, and we put the charge on the outside in the corner. So if he lost 2, then you put +2. If he gained, then you put negative. Okay, easy peasy. Continue to draw the positive and negative ions until the charges cancel themselves out. Okay, the whole name of the game, as always, that crisscross. But we don't call it the crisscross. What's the point of the ionic compound is they're trying to not only cancel out the charges, to become electrically neutral. Because when sodium +1 comes together and has that formation of chlorine, they're trying to get to that neutral compound. Okay, that's the name of the game, electrically neutral. It is proper notation to alternate the positive and negative, which means if you have more than one positive, like maybe 2 magnesiums and 1 chlorine, or 1 magnesium for every 2 chlorines, you're going to want to alternate the symbols. Okay? So make sure whoever X is, and then you put Y, and then you put X, and then whoever Y is, and so forth, so forth. Okay? You'll see when we get there. So let's practice this. If you need some more assistance, these page numbers, these are just examples that I took from the book, and so that way you can see how it happens. So if I take sodium chloride, sodium is +1, chlorine is going to be -1, so we know it's going to be 1-to-1 ratio. But we have to show this formation, okay? So sodium, Lewis dot, has 1 valence electrons, okay? So I like to call this kind of like the before and after. And then he's going to react with that chlorine, and chlorine has 7 valence electrons. And when we put these dots around the symbols, we tend to put the dots where the sodium is missing an electron and chlorine's missing one to become that 8. We like to put them on the insides of each other's symbols, just like that. And when they come together, you have to show something. It's called an arrow. You have to show me the arrow that indicates the transfer of the electron from who gave it to who. So sodium, because he's a metal, he's going to give this one valence electron, and he's going to give it to chlorine. So you show an arrow for that reaction. And then now you're going to get that sodium plus 1, and then you're going to get that chlorine negative 1. So what happens is when you form this compound, you will have Na, and they will literally share, they will share these electrons, okay? And I'm actually going to rewind that because I'm thinking about covalent. This right here, sodium gave, do that little rewind right there. Sodium gave his valence electron to chlorine. So this right here, they have now formed an ionic bond. And it's ionic because it's a metal and a nonmetal. And inside that bond has 2 electrons. They are not sharing it equally. It's just they have electrons between them. What happens is chlorine actually possesses them more. But you'll find out more about that in 8.4 when we talk about polarity. So there are 2 electrons in that bond, but it's not shared equally. Okay, the nonmetals will always possess it more than the metals. And then you have to add these dots, these electrons that were around the chlorine simples because they matter. So let's take this slow. Okay, so sodium chloride right there and chlorine over here. This bond right here, this ionic bond, it is called a specific name, which you're going to see it in 8.3. It's called a bonding pair. It's a pair because there's 2 in that bond. But then these guys on the outside of chlorine, these are called lone pairs, non-bonding electrons. And you will see these 2 terms in 8.3. Okay? So non-bonding are the electrons associated to only that element and not bonded to any other element but that one element. So all of these pairs right here, they have their non-bonding electrons. So if you notice chlorine, where's the octet? Well, he's got those 2. He's got those 2 and those 2, but he has those 2 electrons. He actually has more possession. So there's your 8 valence electrons for chlorine. For the metals, you will never see the 8. Okay? So this right here, it's not shown the 8 valence electrons for metals. You're not really going to see it because the nonmetals possessing the electrons more. But if you did the configuration of sodium plus 1, you would see he has a neon electron configuration, and chlorine has an argon electron configuration. So now write the formula unit for this, and basically you just get that sodium and you get that chlorine with the lone pairs still surrounding the chlorine. Okay? So we are not going to go completely step by step like this. I'm just showing you how to do one, and then we will do the rest. So the arrow, ladies and gentlemen, you have to show me in the arrow how that electron from sodium was transferred to the chlorine. And remember, the metal will always transfer his electrons to the nonmetal. Okay, that's always how it is. Metals lose, nonmetals gain. End of story. Okay, calcium. Okay, calcium has 2 valence electrons. And I got fluorine. Okay, fluorine has 7. So calcium has 2, fluorine has 7 valence electrons. So when you do fluorines, let me do it in a different color. Fluorine only has 1 available spot to bond, and then that's it. But what about this lonely electron for calcium? Well, what happens is, you've done this from the past, calcium's going to lose those 2, and chlorine is going to gain, but he can only gain 1. That's all the only available spot he has. So what happens, ladies and gentlemen, when you crisscross? You're going to get CaF2. So you got to go back to old school chemistry, your basic knowledge of chemistry. When he loses, when he gains, what's that ionic compound? It's going to be CaF2. So what do you have to do? You have to draw 2 fluorines. And this is where rule number 4 is going to come in. You alternate the ions. Okay? So I'm going to draw this over here a little bit better. So calcium has its 2 valence electrons, and we want to put them on opposite sides because we're going to alternate the fluorines. So 1, 2, 3, 4, 5, 6, 7. And then this fluorine, 1, 2, 3, 4, 5, 6, 7. So like I said, we want to leave these lonely electrons. They're going to come together to form a bond, and they're going to come together to form a bond. When you form a bond, you have to have 1 electron from calcium, and you have to have 1 electron from fluorine. They have to give and take. So same thing over here. They're going to come together. So when they come and form that bond, you're going to get fluorine, and he's going to now have 8. We're going to put him in brackets, and then we're going to have calcium, Ca, he's going to lose 2, and then we're going to have fluorine, and he has his electrons. Sorry, it's so hard to draw dots on here. And then that negative charge, okay? So when you're doing these dots, ladies and gentlemen, especially with the stylus, the pen, make sure your dots are very dark, okay? So that is our formula, okay? So you're going to get fluorine, calcium. So I have 2 bonds that calcium formed, and then the lone pairs still stay on fluorine, okay? So I have just created 2 ionic bonds for that calcium fluoride. Let's see if you can figure out what's going to happen. So aluminum has 3 valence electrons. So he's going to lose his 3. And oxide has 6 valence electrons. That means he's going to gain 2. Well, basic chemistry, when I put those 2 together, what will I form? Al2O3. So we're going to alternate our symbols. For every 2 aluminum, I need 3 oxygen. So I'm going to be alternating oxygens, and then I'm going to put my aluminums, because I'm going to alternate them, put my aluminums on the inside, because I need 2 for every 3 oxygen. So with aluminum, my 3 valence electrons, and every oxygen has 6. And actually, I'm going to put that dot right over there. It's because I want to have these lone electrons. I want to have them close, okay? And over here, this oxygen, and I'll put one right there and there. And then for this oxygen, same thing, okay? And then that's what's going to happen, okay? So they're going to lose and gain. So the oxygen, he will complete his octet and have 8, but he's going to gain 2. And this oxygen, same thing. And gain 2. And this oxygen, gain 2. Okay? Now for the aluminums, they're going to lose 3. So with that aluminum, he loses 3, so we put a +3 charge. And then over here, that aluminum, +3 charge. No more valence electrons as in dots. He has valence electrons, but he lost those dots. If you add up the charges, look at it, ladies and gentlemen. You have -2 +3, -2 +3, -2. It's always going to equal that neutral compound, okay? So with the oxygen, aluminum, oxygen, aluminum, and oxygen, okay? And then on here, you will have those lone pairs. So looks like this, and looks like this. Okay? And aluminum does not have the lone pairs. All right? I think you're getting the hang of it. You just need practice. Okay? What if I was going to combine magnesium and fluorine to form a compound? Atoms of which other element would you expect to combine with atoms of fluorine in the same ratio? So what do I know about magnesium? I know magnesium has 2 valence electrons, and I know fluorine has 7. So when they come together, they're going to form, magnesium's going to lose 2, and fluorine's going to gain 1. Well, when I do my crisscross, what's my formula? I'm going to get MgF2. That's a 1 to 2 ratio. Can you predict, is there any other elements that would also form a same ratio with fluorine, a 1 to 2? And I hope so, because basically any element in group 2. Any element in group 2, because they will all have 2 valence electrons, which means they'll all lose 2. So you could pick any element in group 2, and they will all have that same ratio with fluorine. What if I had a mysterious X that has an electron configuration of 1s2, 2s2, 2p5? Okay? Don't think it'll be too hard to figure out who that is. What is the most likely compound that'll be formed between lithium and this mysterious X? Okay? Well, if I look at the periodic table, mysterious X, 1s2, 2s2, 2p5, okay, I believe that's fluorine. Okay? And ladies and gentlemen, always check my work, because Rodriguez, doesn't make boo-boos, but, on the occasion, you never know what could happen, but always check my work. Okay? So this mysterious is fluorine. This mysterious element is fluorine according to the electron configuration. So if lithium has 1 valence electron, and we already know fluorine has 7 valence electrons, what will be that ratio when they come together? Well, lithium's going to lose the 1 he has, and fluorine is going to gain the 1 that lithium just gave him. And when you do that, you're going to get LiF2. I'm sorry, LiF. So 1-to-1 ratio, can you think of any elements that would also form a 1-to-1 ratio with this mysterious F, which is element X? Yeah, any element in group 1, because they all have 1 valence electrons. Okay, they all have 1. And I just want to, I had a moment there, I was trying to remember something. If I scroll back up, ladies and gentlemen, you do need to make sure that you show the arrows. Okay, so for calcium, this one right here, I know I showed you for sodium, but let me do it in a different color. Okay, every time the metals and nonmetals, so for calcium, calcium is going to give an electron to fluorine, and he's going to give this electron to that fluorine. And same thing for the aluminum. The metal, the aluminum, is going to lose and give 1 to each one. Give this one to this oxygen. And same thing, give this one to this oxygen. And give this one to that oxygen. And give that one to that one. Okay? So when you're doing these arrow structures, I apologize, I only showed it for one. You have to always show how the metal's going to lose and the non-metal's going to gain. And it does matter what's called the tail versus the head. The head is where the electron is going. Okay, the tail is where it came from. Okay, so you always want to make sure that you are pointing the arrow in the appropriate spots. Okay, all right, just want to make sure. I knew I'd do it for the first one, but I didn't think I remembered for the other two. We have some properties, and you're going to see a lot more of these coming in Chapter 12, because Chapter 12 is all about properties of solids, okay? Especially ionic solids. Structures determine functions of ionic bonds. And we already know ionic bonds is that metal and non-metal bond between them. Ionic bonds have the following characteristics. They have very high melting and very high boiling points. So let's take a little reminder of what melting is. It is that temperature that melts between a solid and a liquid, so whatever that temperature is. And boiling point is obviously that temperature to get from that change of liquid to gas. Okay, most are solids at room temperature, and there's that word again, 25 degrees Celsius is room temperature. And the reason why, because there's a large difference in electronegativity. And I know you don't know what this word is just yet, because it's coming in 8.4. But what electronegativity is, it's the ability for an element to attract electrons. Notice I didn't say the word energy. It's the ability, okay? Can that element attract electrons more than the others? And absolutely, non-metals love to attract those electrons. So what happens is between a metal and a non-metal, metals have low electronegativity values, okay? They're not trying to get electrons. They're trying to give them away. And non-metals, they have very high electronegativity values, okay? So please do not correlate this to Chapter 7, electron affinity. That's energy to gain the electron. This is a scale. It's an ability. It's a scale that was devised to show which elements want electrons more and which ones don't want them. And like I said, you're going to see this in Chapter 8.4. They're very brittle, okay, which means they break apart. Like they literally can crumble in your hand. So break apart in your hand. Okay, and this is caused by what's called the ion-ion repulsion. Okay, so either the positive or the negative and negative. So that repulsion right there. Many, but not all, are soluble in water. Okay, so definitely are aqueous, but notice it doesn't say the word all though. Okay, when soluble, ions are attracted to the partial charges on water. I think we did this beautiful pictures back in Chapter 4. Okay, and Marlene, shout out to Marlene, had some beautiful drawings of those ions. Okay, giving you a shout out, girl. So remember with water, let's take a little field trip on water. You have, since we're now in the drawing chapter, you have that oxygen and you have these hydrogens. Okay, so whoever this positive ion may be, and it's probably the metal, okay, he's attracted to the O because the O is negative. And whoever this negative ion is, because remember, he gained an electron, he should definitely be bigger, he's attracted to the H, okay? Now, ladies and gentlemen, it's about attraction, okay? When it's an aqueous solution, it's attracted to ions. We're not bonding to ions, okay? An attraction, it's a force. And it's a very, very, very important force in chemistry called intermolecular force. And you will see this in Chapter 11. If you ever mention these words to anyone that ever had AP Chem, I guarantee you their first reaction is they cringe because it's a very difficult topic. So intermolecular forces, it's an attraction to the ions, and it's a particular force called ion dipole. But we'll hold off until we get to that Chapter 12. They're not conductive as solids. So in a solid form, you will see no electricity. But when you get it into this form, yes, they do conduct because you need ions to conduct electricity. So as a solid, like if I just put sodium chloride like in a container, there's nothing happening. But if I throw that salt in water, oh yeah, I'm going to get some conductivity happening. So what it is, it's this key part. It's the mobile ions, the movement of the electrons, because the ionic solids are very rigid. So the moving of the ions around in the solutions, that's what conducts electricity. Conductive in liquids and aqueous solution. So there you go. It's right there again. Okay? The ions are mobile and they're allowed electron movement. And these are explanations, ladies and gentlemen. This is word for word. This is the good stuff. Okay? So if you want to understand how to explain, we need to talk about that movement. Okay? So these are what the structures of ionic compounds look like, and they're usually called a type of structure called crystal lattice. Okay. Ionic compounds, sodium chloride, they form a regular structure in which each sodium ion is surrounded by 6 chlorines. And you can see a picture of this on page 312. So if you notice right here, and it's a little hard when you're looking three-dimensional at this, these little guys, let me try to find a spot for you. All right, so if you look at the repeating pattern, okay, and we talked about this before, this repeating pattern, crystalline structures. If you notice right here, these little purple ones, oops, purple, those are the sodium because they are smaller. They lost an electron. Probably should do this in black. And then these bigger ones, these green ones, those are the chlorines because they gained an electron. And chlorine definitely has more electrons than sodium does. And if you notice it, focus on this purple one right there. He's got a chlorine, a chlorine, a chlorine, a chlorine. He's got 4 surrounding it, but what you don't see is on the inside there's one, and then on the outside there's another. So for every 1 chlorine, you have 6 for every chlorine you have 6 surrounding sodiums, and for every 1 sodium you have 6 chlorine surrounded. So it's always a 1 to 6, even though we have our formula is +1 and -1. But when you actually build the structure, this crystal 3-dimensional structure, you have for every 1, 6 surrounding it. So there's a regular arrangement of it, an alternating arrangement, and it's called, like I said, crystal lattice, crystalline structure. Okay, and notice how the ions are very, very, very tightly packed together, and they will have those very tightly packed structures compared to like covalent. Sometimes they're far apart, the molecule ones versus ionic. So in 7.4, let's get to some energy. How is this whole thing about trends? How are they related? So recall that 7.4, aka ionization energy, okay? The loss of an electron from an atom is always an endothermic process because you always need energy to lose that electron. You always, always, always need it. So removing that 1 electron from sodium in the gaseous state to form ion in the gaseous state requires 496 kilojoules per mole. And this information is just got from 7.4. But in 7.5, called electron affinity, okay, the energy to gain an electron, it can be positive or negative, okay? So what happens is, usually for nonmetals, it's a very exothermic process. So right here, it's giving off energy as it accepts an electron, as it gains it, okay, as you saw by this equation right there. So these elements started with no energy, and then they came together and did a reaction, and bang, kaboom, explosion. And you got this negative reaction, exothermic. So when it produced that compound, it gave off energy. Okay, and that's why you saw the bright light from the video. So what happens is, why is this actually as stable as the attraction between the ions of opposite charges? So this attraction draws the ions together, and it releases energy, causes the ions to form this what's called crystal lattice. And this word lattice is going to be very, very important in just a second, okay? Because I know this is something you haven't heard before. A measure of how stabilized results from arranging these oppositely charged ions in this ionic compound is called lattice energy. So the stabilization that happens after these ions form the solid, it's the energy required to completely separate 1 mole of a solid ionic compound into the gaseous ions, okay? So I know you saw that word mole. You probably got a little excited. You thought we're doing a little bit of math. Sorry, not yet, okay? Not yet. But I need to teach you how to write the equation, okay? So what we do, it's the energy required. That means you need energy, positive, okay? To take that 1 mole, so it's got to be a coefficient of 1. It's got to be a coefficient of 1. And separating it into the gaseous ions, okay? So very, very key, because I know you're used to sodium as a solid. I get you, okay? But it has to be an equation that's in that form, okay? So to envision this process, if we took sodium chloride, imagine the structure that you see right there above, and so that the distances between the ions increase and the ions are far apart. So we take these very, 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 very close ions, and then now we try to separate the ions. We're trying to break those forces apart. And when we break those forces, aka the bond, always, 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 you need energy. And there you go. That's why you see this positive. So remember, delta H is the energy, lattice is the structure, ionic compound. So I'm going to put the word ionic for that word lattice right there. And you need energy to break that bond. So that energy right there is to take that sodium and chlorine bond right there. That's how much energy you need to break it. But here's the cool part. What if we wanted to form sodium chloride? So if we take this equation and we what's called reverse it, aka flip the reaction, flip the equation, and now I take my gaseous ions and form that 1 mole of solid compound. Look what happens now. Now that I formed it, my energy, oops, I don't have to write the number, it's right there, it's negative. So if one way is positive, when you flip the equation, it's a change of signs. Ladies and gentlemen, the point is, let's don't memorize numbers, but let's understand that if you form a compound or if you break a compound, do you need energy or are you releasing energy? So anytime, big, bold, please. Anytime, and I know I just did blue on top of blue, anytime you break a bond, you always need energy. It will always be endothermic. But anytime you form a bond, it is endothermic. And that energy will be positive. So hopefully, ladies and gentlemen, you see the difference of forming bonds or breaking bonds. It's always a reverse process, endothermic versus exothermic. Now this last part is all about the trends. If you did very well on Chapter 7, then this should be a piece of cake. Because if you can explain the trends, then you have this. Now, if we didn't do so great on the trends, well, then we got some work to do, okay? But we'll do it together. Unit 1.8, explain the relationship between the trends and the reactivity, I almost said radioactivity, the reactivity of elements and periodicity. Periodicity is a fancy way of saying the trends to the periodic table. Typical charges of atoms and ionic compounds are governed by their location on the periodic table and the number of valence electrons. So basically, we all know if they have one valence electron, they're going to lose that one valence. If they got 7, they're going to gain 7. Now, it really helps. Take a minute, open your book, okay? Because in the book, it really helps if you have some values in front of you, okay? And I don't think I was able to get the values in here. Nope, I wasn't able to get them in here, okay? So lattice energy depends on the charge, on the ions, and the size. Ooh, I think this guy kind of is a little familiar, aka ionic radius. Because we're talking about ions. So we're talking about they've already lost or gained. So the charge, the plus or the minus, but now the number. How big is that number? Is it a 1, a 2, a 3, whatever it may be? So lattice energy, very, very important. It depends on 2 things. Okay, and I'm going to highlight that in a different color because I want you to understand how big that guy is. So page 303, have some numbers in front of you. Okay, because I'll try to do my best with some numbers. List the lattice energies for the number of ionic compounds. Okay, so they gave some ionic compounds looking at either the same metal or looking at the same nonmetal. Large positive values indicate that the ions are strongly attracted to one another in ionic compounds. The strong attractions also cause most ionic metals to be very hard and brittle with high melting points, like sodium chloride. Sodium chloride melts at 801 degrees Celsius. I want you to put this in perspective. You know Mr. Water? Water melts at 0 degrees Celsius. The melting from a solid to a liquid melts at 0. This is 801, okay? So, yeah, we're talking about very hot, okay? And I guarantee you the stove is not doing it, okay? So let's look at table 8.2, which is the top of page 303, and then on the table of 304, okay? I want to see if you can see some trends. Because if you can see the trends, you can explain it, ladies and gentlemen. It's that right there. The large positive values indicate that the ions are strongly attracted to one another, and that's why the temperature is so high. That's how the energy is so high. So look at the magnitudes of charges if you have the same cation, different anion. Okay, so here we go. Let's look at these. So lithium chloride or lithium fluoride, lithium chloride, and lithium iodide. Okay. And if I write down the numbers, and these are in kilojoules, 1030 kJ, and then 834 and 730. Now what do you notice? Okay, now these energies, this right here, this is lattice energy. Okay, and remember, what does lattice energy measure? Okay, lattice energy is the energy required to break that compound up into the gaseous ions. So this number right here is that energy to break the bond, to break that one bond that's holding them in there. What do you notice about the trend? Same cation, but look at these guys, halogens. If you notice their position on the periodic table, okay, if you notice Mr. Periodic Table, you got fluorine, and we got chlorine, and bromine, and iodine. Let's talk about size, okay? When these guys form ions, so ionic radius, they're all going to have negative charges, so they're all the same -1, okay? But what is the size? What's that trend as you go down the group? Well, as you go down the group, doesn't the atom, the ion, get bigger? So atoms, ions down here, these are bigger ions. And fluorine, very small ions. And why was it small and big? Fluorine, less protons, valence electrons. close to the nucleus. His valence in N equals 2. But Mr. Iodine, that's got his valence electrons all the way out there, higher quantum number, farther from the nucleus. So what do you notice? Okay, you have to mention the charge of the ions. So they're all negative ions, and they all, not only -1, well actually I'll just put, they're all -1 ions. But what do you notice about the size of the ion? But the size of the ion changes. Okay, so what do you see? The bigger the anion, so the bigger the anion, that negative charge, the larger the energy or the smaller the energy. And if you notice right here, Mr. Iodine, he's the biggest anion up here, but it has the smaller lattice energy, which means to break this one, you don't need a lot of energy, okay? To break fluorine, because he's smaller, his electrons are closer to the nucleus, you need more energy to break that bond up. You see a little Z effect kind of coming into this too, okay? It's literally, it's chapter 7, but just looking at a different trend. So the bigger the anion, less energy needed to break that bond, okay? It doesn't matter, ladies and gentlemen, if I look at lithium or I look at sodium, same thing. Let me get the numbers for sodium. We'll change the color here. Right on that same table, if I pick the same one, sodium fluoride, sodium chloride, sodium bromide, all +1, all -1, but I'm just changing who the anion is. Who do you think is going to have the highest energy to break the bond? Who's going to have the lowest? Okay, smaller the anion, more energy. And notice 910, 788, 732. Okay, same thing, ladies and gentlemen. You're not telling me as I go down the group the atom's getting bigger. Okay, they don't want to hear about that. They want to hear that the anion, they all have the same -1 charge, but the size of the ion is changing. So the bigger the anion, the smaller the lattice energy to break the bond. That's it. Literally, that's it. Okay, you want to talk about Z effect? Go ahead. You want to talk about the quantum number? Absolutely. Okay, but make sure you get to the point. So let's try a different trend. What if and notice right here, it's the same magnitude of charge. And what we mean by that same magnitude of charge, we mean +1, -1. Okay, so +1, -1. Same thing over here. Same magnitude of charge, but now I'm going to keep the anion the same, but I'm going to change the cation instead. Okay, so if you notice in this one, let me see if I can pick one. Okay, so right here, this is where page 304 is going to come in. So you can see where I'm getting these numbers. So if I take lithium chloride, and all I do is keep chlorine the same, but just change the metal. So sodium, potassium, I can even keep going, rubidium, okay? Now, what are you going to notice in the trend? Let me show you lattice energy. So the lattice energy, you're looking at 834 kilojoules and 788 and 701, 697. Ladies and gentlemen, it's the same thing. Small cation, big cation. The bigger the cation, the smaller the lattice energy needed to break the bond. Same story, I just took one word out and changed it. So, the larger, and actually I like that word better. I've always hated that word bigger. The larger the cation, please make sure you say cation, because that does make a difference. The larger the cation, the smaller the lattice energy needed to break that bond. So if you have a big cation, you need more energy. Okay? And ladies and gentlemen, it's about that attraction. The protons, the electrons, those electrons are so close to lithium. I mean, you're talking about 1s2, 2s1. Those valence electrons are very close to lithium, and lithium is holding pretty tight on it. So if you're going to break that bond, you need more energy to break it compared to rubidium chloride. Well, if you're going to change the metal and change the nonmetal, what happens if you change the charge? Okay, so here's the next one. So remember up here, lattice energy depends on the charge and the size. Well, we looked at size, but now what happens if we change the charges? So let's now, I say +2 versus a -1. So different cation, but the same anion. And I'm going to look at same page, page 303 for these values. So let's say I have magnesium chloride, where magnesium is +2 and the anion is -1. And if I want to look at strontium chloride, which is also +2 -1, let's see what's going to happen. 2,326, so lattice energy in kilojoules. And strontium, let's see, bigger ion, smaller ion. Think that energy is going to go up, or you think that energy is going to go down? And I hope you're guessing goes down, because bigger the ion, the smaller the lattice energy. Okay? But I want you to also see this. Look at these. Twice as much, or even look at the over here. More ions, less ions. You have more negative anions, but over here you only have one. And look at what happened to energy. It practically doubled, and more than doubled. Okay? So when you have different charges, okay, requires even more energy. So when you have what's called like a 2-to-1 ratio versus a 1-to-1 ratio, that 2-to-1 ratio or 1-to-2, whatever you're going to do, because you have more ions, this one has more ions. You actually have 3 ions over here versus 2 ions over here. So in case you don't see why it's 3, because remember right here you have magnesium. Magnesium is his own ion. And then I got chlorine that's an ion, but then I have another chlorine. I have 3 ions over here versus over here I only have 2 ions. More ions, more energy to break that bond. Okay? So they can ask you to look at any comparison. Same charges, different charges, size. You always have to relate back to chapter 7. Okay? So if I do one more trend, same magnitude, but now let's go a +2 and a -2. Let's compare these two. Okay? So what if I now have my ratio? What if I do my ratio now 2-to-2? I now have 4 ions, where over here I had 3 ions. Let's see what's going to happen to energy. So if I look at page 303, let's look at these ones. Magnesium oxide, calcium oxide, strontium oxide. And I would give you all the numbers, ladies and gentlemen, that you need, but you have to explain what the numbers mean. Okay? So let's see. If this right here, magnesium chloride, was a 1-to-2 ratio, and now I'm going to magnesium oxide, which is a 1-to-1 ratio, okay, but it's +2 -2, okay, and actually I need to change this right here. I don't mean 4 ions. I mean, sorry, I got ahead of myself. A 2 to 2 ratio. I don't mean 4 ions. There are only 2 ions over here. A +2 and a -2. So let's go a little bit back there. The ratio is 2 to 2, as in +2, -2. Okay, but when you break that down, it's still a ratio of 1 to 1 because I see 1 magnesium, 1 oxygen. So you still have 2 ions in this compared to 3. But it's this thing called the magnitude, the size of those ions. It's a +2 and a -2 versus over here is a +2 -1. Okay, the magnitudes are not the same, but over here the magnitudes are the same, but they're bigger magnitudes. And I know I hate that word, should be using greater. Okay, do you think this number over here for magnesium, do you think it'll be less or greater than that 230.26? Will it be less or greater than that 23.26? Okay, and I hope you're guessing greater, because the larger the magnitude and sizes, the more energy needed to break that bond. So if you actually see the numbers for magnesium oxide, it is 3795 kilojoules, and calcium 3414, and then 3217. Okay, you're talking about over 1,000 kilojoules different. So the larger the magnitude in the ions, even more lattice energy needed to break the bond. Regardless, ladies and gentlemen, you always need energy, but the name of the game is who requires more energy? Smaller atoms, bigger atoms, smaller charges, bigger charges. All about these two right there. You have to now mention, we got so used to talking about Z effect and N. Okay, that's the trends. Now we have to talk about these two words for lattice energy: size and the magnitude of the charge. Okay, so when they say magnitude, ladies and gentlemen, they're talking about the actual number, the value of the charge. A +1 versus +2, +2 is bigger in magnitude. Okay, so right here, okay, a very, very important, I cannot stress how you will see this diagram on the AP test. And it's going to relate energy as in when you break the bonds apart and as you come together and form those bonds. Doc Dina has a beautiful little tiny video, okay? And let me show you on Teams real quick. Let me get it up. So you're going to watch this video. And Doc Dina is also a grader of the AP test, and she will actually even tell you her experience when she reads students' free responses for this. And students are very unsuccessful when they're explaining this. So this diagram is beyond important, okay? I cannot stress, and I'm even like under, I meant to highlight, super important about how the energy needed to break the bonds versus energy to form. Which one needs more energy, forming bonds or breaking bonds? So you're going to watch this quick little video of here, and if you notice on the Teams, let me bring it right on over. Over here, you will see it on the next page, right there. Quick little video, and she goes straight through how to do this, how to read one of these diagrams. And every year on the AP test, it's on there. So I'm stressing to please pay attention to the document. So pay attention not only to the diagram, but how to explain this thing called energy. Okay, and it's got a particular name called potential energy. And potential energy, the energy at rest, and you'll hear her talk about it. Okay, She's going to go into this equation also. This is Coulomb's law. This is his actual equation. Thank goodness we don't have to do his equation. But you're going to hear her explain how students use this equation to explain that diagram. I strongly suggest don't, but you can if the equation makes sense to you. You're going to not see her solve anything. But the point is this. It says Q1 and Q2 are the charges of the particle. One of them's positive, one of them's negative. Okay? K is Coulomb's constant. Don't need to memorize the number. And R is the radius. Okay? Radius squared. Okay? It's the distance. So we're talking about radius. Atomic, or actually ionic radius. Okay? And then F is that force. That force that is between those two particles. Okay? So like I said, not doing the math, but some students like to use this equation to explain. And if it makes sense to you, that's fine, but make sure you explain it correct. So the magnitude of lattice energy for an ionic solid depends on the charges of the ions, their sizes, and the arrangement. That is literally all about lattice energy. You change the charges, +1, -1, +2, -1, +2, -2. That's what we call the magnitude of the charges. And if you change the sizes, okay, we already know how to change the sizes, and the arrangement, okay, that crystal lattice arrangement. So you're going to watch that video, and it's going to help you, because this is the learning target, ladies and gentlemen. Coulomb's law indicates that the attractive interaction between two oppositely charged ions increases as the magnitude of their charges increase. Now you just saw this. A +1 versus a -1 versus a +2 and a -2. That magnitude of charges increases energy. Okay? So right there, you definitely will have an increase in lattice energy versus a +1 and -1. And the distance between their centers decreases, which means these two ions, these ones right here, they are further apart from each other, but the magnitude, if it's a +2 and a -2, you'd actually have the +2 and -2 smaller distance between each other. So when they have opposite charges and the magnitude increases, then you will have a smaller radius between the atoms, or actually the ions, sorry. And over here, you would have a larger radius between the ions. That's all about Coulomb's law. So you're seeing it again. 2.2. Represent the relationship between potential energy, called PE, and watch Doc Dina's video. She does an excellent job at it. And based on the factors of those interactions. Because the interaction strength is proportional to the charge of each ion, larger charges lead to stronger interactions. That's a good trend. Because the interaction strength increases as the distance between the centers decrease, which means they get closer together, smaller ions lead to stronger interactions. Ladies and gentlemen, that's your explaining. That is the explaining. Okay? So you have everything you need to explain. Okay? So if we do an example, as you read right here, lattice energy decreases as you go down the group. Lattice energy decreases as distance between ions increases. This is not trends as you're going down the periodic table, it decreases. This one's totally fine. But be very careful with this one. Do not say something like this on the AP test. Okay? You need to be referring to the charges and the distances. Okay? Just letting you know, as you go down the group, it decreases. Okay? So anytime in a group, lattice energy will decrease as size of the ions increase. So lattice energy will decrease. And actually, let me put it in words because I don't want you to think of that arrow like that. So lattice energy decreases as the size of the ion increases. The greater the charge, smaller the radius, the stronger the force. Great explanation right there. Okay? So if we did an example, after you watch Doc Dina, arrange the ionic compounds without having any numbers of the following, and they want an increasing lattice energy. So the first thing is, ladies and gentlemen, look at the charges that they have first. Sodium's going to lose, +1. Fluorine's going to gain. Cesium in group 1, he's going to lose 1. Iodine, going to gain. But now look at these two. Calcium +2, because calcium's in group 2. And oxygen is also -2. Okay? Lattice energy increases when the charges increase. So if you notice right here, larger magnitude and charges. Okay? So out of all of these three, I absolutely know who's going to have the largest, and this one is definitely going to have the largest because the larger magnitude and charges. I'm not even looking at these two because they're +1, -1. So he is definitely going to be the largest. So now it's going to come down to size for these two because they have the same charges. So now for these two, size is going to determine it. So what do we know about sizes? Lattice energy decreases, as you're looking right over here, lattice energy decreases as the ion size increases. I mean, look at these elements, ladies and gentlemen, where they're at on the periodic table. If I drew kind of like a little generic periodic table, okay, you got sodium up here, and you got fluorine. Over here, I got cesium, huge atom, iodine, huge atom. If they come together to form a bond, big radius, okay? Big distance between them, smaller distance between them because they're smaller atoms. And what do we know? The smaller the ionic radius, the stronger the attraction, okay? So who is going to have the least, the bigger the radius, the less lattice energy? Because cesium, iodine, has a larger radius, distance between them, is going to have the least lattice energy. But sodium fluoride, has a smaller distance between them, will have a larger energy than the cesium iodine. Okay? So first, ladies and gentlemen, I always look at the charges. Do you see a difference in charges? That's the easiest. Then go to sizes. Bigger atoms don't require as much energy. Smaller atoms, because their attraction, remember that attraction? Their attraction between the protons and those electrons are very strong. They're very close together. The smaller the radius, the stronger the attractive forces. And that is what makes the greater lattice energy. Okay? So right here, I know you thought this video was ending soon, and I apologize. It's a big topic. AP Classroom 2.1, 2.4, you got Mr. Fairbra that's going to help you with the sample AP question. So if you go on Teams, okay, as always, Mr. Fairbra, and find the video for Unit 2, College Board videos. And if you go to the one 2.1, 2.2 right there, and scroll to about 33 minutes, you're going to see a past AP question, okay? And he's going to help you with that. You're going to make a prediction about these two. So if you know sodium fluoride, could you make a prediction regarding these? And it's literally what you just did. So do you predict if it will be less than 930 or would it be greater than 930? And justify with properties and Coulomb's law. If AP wants you to talk about those two things, then you better talk about those two things. Okay? So electron configuration, I think we have beat to death electron configuration. Okay, just remember lattice energy increases as the charge increases. So real quick, if you have a +1 versus a +2, that lattice energy will be greater for that +2 because it's a larger charge. Okay. The second electron removed, so I'm looking at sodium, comes from an inner core electron. And we already know with ionization energy, if you take a core, you need a lot of energy. Okay, we've already done these, ladies and gentlemen. Okay, I don't think we need to beat this to death. Okay, these right here, I would like you to do these, and you can check your answers right there. Page 306. I know it's a very, very long video, okay? But see if you can actually predict and then check your answers. Transition metal ions, okay? Because ionization energies increase rapidly for each time an electron is removed. You always make sure when you're doing electron configuration, whoever that noble gas is, and then you would get a quantum S2, and then you would get the quantum -1, the period -1, and then you hit the D block, and whatever that number is. You always come after the higher energy level before you